All right. This is CS50, Harvard University's Introduction to the Intellectual Enterprises of Computer Science and the Art of Programming. My name is David Malin, and I actually took this course myself back in 1996. I was a sophomore at the time. I was actually concentrating in government because a year prior, as a first year, I'd come into Harvard thinking that I liked history and constitutional law and sort of similar classes in high school. And so when I got here, I rather gravitated toward that which was familiar. I figured if I liked and if I were good at that particular subject in high school, then that's presumably who I'm supposed to be here. But it wasn't until sophomore year that I got up the nerve to step foot in the CS50 classroom. And even then, it was only out of curiosity. Like, I had no intention of studying computer science, of even taking CS50 when I got to campus. But people were talking about it, and there was a lot of like, beware, and it was perhaps for the initiated only, and I didn't really know ultimately what computer science was. But for me, the sort of light bulb went off, and I found that contrary to what I had seen in high school, where I saw friends of mine like programming away in the computer lab, heads down, sort of antisocially, just doing whatever it was they were doing, it really wasn't that once I got to this particular class in this particular place. It was much more about problem solving more generally, and just learning how to express yourself in code in different languages so that you can actually solve problems of interest to you, even if you have no intention of being a computer scientist or an engineer, but just want to be able to solve problems, analyze data, do interesting things in the arts, humanities, social sciences, physical sciences, or really any other field. And indeed, this particular path led me to computer science, but the hope for CS50 more generally is that indeed you just find your way to applying principles that you'll learn over the coming months to whatever field is of interest to you. With that said, it was definitely a lot of work, and not without its frustrations for me, but there was no better feeling than like banging your head proverbial against the wall for some number of hours, even days, trying to fix a bug, a mistake in your code. And then, oh my God, the rush of emotion, of accomplishment, of pride, of exhaustion when you finally solve some problem that's really been weighing on you. It's just so incredibly gratifying, but also empowering. Because unlike a lot of fields, like computer science was built by humans themselves. And so if a human built this, surely you, another human, can understand it as well. And so even though there's going to be some distractions along the way, you're going to see what looks incredibly cryptic if you've never programmed before over time. And with practice, everything just starts to make more sense. And with time and with practice, you just get better at this particular field. And indeed, really, the key to success in programming in general is just to allow yourself enough time. And so at least, thankfully, I quickly got into the habit of starting early in the week, for instance, when writing actual code. Why? Because you're going to like run up against a wall. You're not going to see some bug. Something's not going to jump out at you, and that's fine. That's when you sort of call it a day, take a break, move on to something else, and then just come back to it. And that's what keeps programming fun for me, even all of these years later, whether it's teaching or actually applying it. But there's down the road a history of an MIT hack, and it looked a little something like this in yesteryear. And there was a little sign the MIT students, when they made this hack, on the wall that says, "Getting an education from MIT is like drinking from a fire hose," which indeed they have connected to what should have been otherwise just a water fountain. And that's going to be what it feels like sometimes, not just in computer science per se, but just an unfamiliar field. If you're not from STEM, if you're not from CS, that's fine. But so much of it ultimately is going to be absorbed by you and going to be within your grasp by term's end. So just keep in mind that's very much the intent, but you'll be amazed what you're able to create, to accomplish just 3 or so months hence. Indeed, 2/3 of you, contrary to what you might think or assume, have never taken a CS class before. So it's absolutely not the case that the person to the left and to the right surely must know more than you. Indeed, it's quite the opposite. And as you'll see in the coming weeks, as you write your own code and solve your own problems, what ultimately matters in this course is not so much where you end up relative to your classmates, but where you end up relative to yourself when you began. And it really is all about that delta, whether you've programmed or not, just getting something out of a class like this. And if it does take time, and if you do feel those frustrations, but you simultaneously eventually feel that sense of accomplishment, that just means it's all working. And indeed, hopefully, all the more worthwhile and gratifying ultimately as a result. So what are we going to do in the coming week? So here we are in week 0. We'll soon see why computers and computer scientists start counting, if you will, from 0. But week 0 is one in which we explore computational thinking, sort of thinking like a computer and starting to clean up your thought processes, getting you to think, to solve problems more methodically, and then ultimately translating that into code. And some of you might recognize this environment here, aka Scratch, coincidentally also from MIT. You might have used it in grade school. We'll use it today and a little bit this weekend in the course's first homework assignment or problem set, but not so much to kind of play around in a way that you might have if you did use it in yesteryear, but to explore ideas of computer science and programming that we're going to use and reuse every week hereafter as well. Thereafter, we're going to transition just next week to week 1, so to speak, whereby we'll introduce you to a more traditional language, a lower level language, an older language called C. And in C, you're going to use your keyboard, not so much your mouse and pointing and clicking, but you're going to write code that soon is going to look a little something like this. And if you've programmed before, you can probably glean what this is going to do. If you've never programmed before, which is the case for most of you, this too will soon make sense. But this is the most canonical program that most any programmer ever writes, called Hello World. And indeed, that and all of the surrounding syntax above and below just that sentence, Hello World, will soon make all the more sense. You'll learn how to use industry standard tools, so to speak. Pictured here is something called Visual Studio Code or VS Code. You'll use a cloud-based version of it initially, so you don't have to suffer with any technical difficulties or headaches like that. It'll just work right off the bat. But we'll use that tool and others ultimately to then explore ideas in computer science, principles that you can apply. And we'll take a look underneath the hood, so to speak, of your computer at your memory, or RAM, random access memory, where all of the data is ultimately going to be stored. We'll also take a look thereafter at bugs. A bug is a mistake in a program. Here is an actual bug in an actual computer in yesteryear. But we'll teach you how to debug programs, find your own mistakes, find others' mistakes, and improve that code as well. We'll transition then to algorithms, step-by-step instructions for solving some problems, which we'll touch on today too. And if you picture here, this is actually a pretty representative problem. Odds are you haven't had to deal with something like this, but it's representative sorting, for instance. If you think of each of these small bars as being a small number, each of the bigger bars as being a bigger number, you might wonder, well, how could you as a human sort all of these bars? Like get all the short bars over here, all the big bars over there. Well, odds are if you're like me, you would probably kind of eyeball it. And if you could physically interact, you might just start grabbing the smallest elements first, put them over on the left, maybe grab the biggest elements, put them over on the right. But what's your algorithm there? Like, how would you teach someone younger than you who's never done that before how to do it? How would you compel your Mac or PC or phone to do something like that? You can't just kind of wave your hand and say, oh, figure it out, move things around. You have to express yourself more methodically. So we'll translate even ideas like this into code too. And that's what the Googles and others of the world are doing constantly as they sort and organize the world's information. We'll use metaphors along the way if it helps. We'll talk about your computer's memory as kind of being like a postal address. Like every mailbox in the world has some form of postal address, street, city, state, country, and the like. And it turns out that's how your Mac, your PC, and your phone also work. You've got a whole bunch of memory, like the picture before, but you can think of it really as individual mailboxes. And you can put anything you want in those mailboxes, and you can go to a mailbox to grab information that's from it. So at the end of the day, that's really all your computer's doing with information. It's just kind of organizing it, not into mailboxes per se, but a term you probably know called bytes, for instance, instead. we'll talk about problems that arise, even nowadays. In fact, most of you are familiar with your Mac, PC, even phone, like spontaneously rebooting sometimes, crashing, the little annoying spinning beach ball or hourglass icon that happens. Like, what is with that? Well, those are just bugs in programs that humans at Apple and Google and Microsoft and others, they screwed up. And they wrote buggy code, and your computer, when it encounters those mistakes, doesn't know what to do. And so 9 times out of 10, so to speak, it just crashes or freezes or the like. But that kind of stuff will make more sense. So even the real world will make sense. And pictured here are some lower level terms we'll eventually get to mid-semester. But generally speaking, when something is going this way, as per this arrow, and something is going this way, as per this arrow, like that does not end well. And that often is what happens when your computer crashes. Someone's using memory up here, but someone else is using memory down here. And then they're not really talking left hand and right hand. So that is just a high-level overview of some of the problems we'll encounter. But we'll focus too on data ultimately. So pictured here is something fairly technical called a hash table. It's an amalgam of something we're going to soon call an array and also something we call a linked list. And these are just fancy terms for describing how you can organize information even more flexibly than just putting individual values in mailboxes. Like, how could you build structures, like actual data structures, so to speak, two-dimensional structures at that? And so what you're seeing here is a glimpse, as some of you might have recognized, of some Harry Potter universe names, but they're organized somewhat alphabetically. And notice that anytime there's multiple people with a name that starts with H, like Hermione, Harry, and Hagrid, well, they can't all fit in that mailbox if each of these squares along the left is that same mailbox. So you have to kind of chain them together. Well, we'll learn how to do that in code so that even if you get more data than you expect, if your business is booming and you're some web-based business, how do you keep adding and adding information to your software to actually keep up with it? But this, again, is what code's going to soon look like, as soon as next week in week 1, this here being C. But we'll transition in a few weeks to a more modern, higher level language, so to speak, called Python. Indeed, the course very deliberately, back in my day and now this, introduces you first to C, which, funny enough, many people don't tend to program in certainly every day. I use C generally September, October, November, December when teaching CS50 itself, but it's everywhere nonetheless. In fact, even today's other languages with which you might be familiar, like Python and Java and yet others still, use C, this same primitive language underneath the hood, because it's so darn fast. And as you'll learn over the coming weeks, it really gives you access to and an understanding of what's going on conceptually down here, so that thereafter, after CS50, when you're writing code, you can sort of think at a very high level what's actually going on. So in fact, in just a few weeks, what looks like this in C is going to look instead like this in Python. And you'll better understand what's going on underneath the hood. And odds are after this class, you'll reach for a language like Python more frequently than C, but you're going to benefit from that bottom-up understanding thereof. Thereafter, and towards term's end, we'll introduce you to a few other ideas, like where do you put large amounts of data in things called databases. Not things like spreadsheets like here, but actual databases where using those same kinds of data structures, you lay things out in an interesting way in memory. Thereafter, we'll transition to a very familiar environment that you and I use every day, the web. Like the web has become rather the user interface or UI that we use everywhere on the laptops, desktops, and even mobile devices nowadays. Well, pictured here is a language called HTML. It's not a programming language. It's a markup language. And some of you might have made home pages or portfolios in the past. But you'll understand what's going on here. But more powerfully, you'll understand how the computer sees that same kind of code, builds up a hierarchical family tree type structure in memory. And then you can manipulate that tree with code to actually add more and more information, chat messages, anything on the screen that you like. And finally, we'll tie all of this together by introducing what are called frameworks and libraries, third-party code that makes it a lot easier to solve problems of interest to you. And so in particular here, this is the very first web app that I myself made back in like 1997. I was part of the first-year intramural sports program, not as an athlete, but as the programmer. And I was teaching myself how to build web applications. I only knew C and maybe a little bit of something else at the time. But this became, for Harvard at least, the very first website for the first-year intramural sports program. And it wasn't just a static website with links and images and the like. It was interactive. You could register for sports. We could input exactly who was in a tournament bracket or the like. And it could actually automatically keep track of this data. So there, too, after just 3 months of a class like this, you'll go from writing quite simply this week and next hello world to building things like this for whether it's web, mobile, or other platforms as well, if you so choose. But we'll get you off of the course's infrastructure by the end of the term. You won't be using any toy environments along along the way will empower you ultimately to write code after CS50, especially if this is the only CS class you ever take on your own Mac or PC using the same software, but not the cloud-based version thereof. But all of this software is itself free and can be used by you powerfully after the course's own end. But along the way, as you may know, is there this tradition within the class, particularly in healthy times, of a number of events that really brings people together, not just collaboratively academically, but to just solve problems and generally engage with each other as well. Coming up first, CS50 Puzzle Day, which is meant to be not jigsaw puzzles, but logic puzzles that require no prior experience with computer science or programming, but it's just an opportunity to sort of quietly work on a packet of puzzles with some number of friends for prizes and more. Later in the semester, once you tackle your final projects, the capstone of the course, where we don't give you a homework to write, you yourself come up with something to build. We'll get together generally around 7 p.m. in the evening, wrap up around 7 a.m. if you so choose, and it's an evening, a 12-hour opportunity to collaborate with classmates on your very own final project in a large space on campus that ends, if you're awake with us, at 5 a.m. We can hop on some CS50 shuttles and go down the road for some pancakes at IHOP around 6. Of course, this is 6, 7 a.m. at that point, but it's an opportunity finally to lead into what's called the CS50 Fair, which is an end-of-semester celebration and exhibition of everything that you'll accomplish over the coming months. And in fact, pictured here are some of your predecessors in healthy times. The CS50 Fair allows you to come with your laptop or phone and exhibit to students, faculty, and staff across campus, put together something in person and on video that people can delight in seeing as you exhibit what it is you created and what you learned over the course of the several weeks, and ultimately a chance to just share and inspire others as well. And you'll all walk home ultimately with your own I Took CS50 t-shirts saying as much as well. So with that high-level overview of the course, I propose that we begin to take a look at what computer science itself is and what it is we're going to be doing over the next several weeks at this lower level than 2. So what is computer science, right? If you're maybe like me or new people like my friends in high school, you probably assume that it means programming. And that's absolutely a big part of it for a lot of people, because with code you can write, you can express ideas and solve actual problems, especially involving data. But computer science itself is really the study of information, if you will. How do you represent it, and how do you actually process it? And in that sense, computational thinking is just the application of ideas from computer science, a course like this, to problems of interest to you. Again, in the arts, humanities, sciences, social sciences, whatever the domain of interest is to you. So with that, if computer science is all about information and with it the solving of problems, well, what does it actually mean to solve a problem? Let's see if we can't propose a model into which all of the lessons learned will ultimately follow. And I'd propose that this is problem solving. You've got some input, which is like the problem you want to solve. The goal is to solve it, so that's the so-called output. And then somewhere in here, the proverbial black box, is some kind of secret sauce that gets the work done. And in the coming months, we'll have to decide, well, how are we going to represent these inputs and outputs? And really, how do we code up? How do we write solutions for what it is that's solving the problem of interest to us? So when it comes to representation of information, there's a lot of ways we can do this. And for instance, if the problem at hand quite simply is to take attendance at the beginning of class on the first day of school, well, how could we go about doing this? Well, we could actually use a system called unary. Well, what is that? Well, that's a fancy way of saying 1, 2, 3, 4, 5, maybe 6, 7, 8, 9, 10. And I can use my digits, pun intended, on my fingers to actually count everyone up. And eventually you need toes and whatnot if you have to count so high. But unary is a very simple system of using a single symbol, a human finger in this case, to just solve some problem, like counting the number of people in the room. Let's make this slightly more technical for a moment, a little more mathy. That's just called base 1, where the base under which you're operating has 1 digit in it, like literally a human finger, and maybe multiple such fingers if you need to count higher. But of course, most of you, if not all of you, generally vaguely know that computers use something other than unary. And even you and I probably don't use this that often. They use what language or alphabet instead? Yeah, so binary. So binary is indeed the system that computers somehow use. So in this case, bi implying 2. And so computers have 2 digits, it turns out, at their disposal. And in fact, if you've ever heard the technical term bit, which is like a smaller version of a byte, more on that soon, well, a binary digit is the origin of that term bit, because if you get rid of some of the letters and you're left from binary digit with just bit, thus is a bit. A bit is just a 0 and 1. It's 2 more digits than you might have on your own finger. And of course, it's fewer, though, than you and I have. You and I typically use, as humans, the decimal system. Dec meaning 10, because you and I generally use 0 through 9. So on the one hand, another pun intended, you've got unary. Computers use binary. We humans generally think and talk in terms of decimal. But at the end of the day, these are fundamentally going to be the same thing, which is to say that it's all pretty accessible to us. Even if you're not a computer person, I dare say you're about to be. So what is a bit? Well, a bit then is a 0 or a 1. That is a so-called binary digit. But how do computers only speak in binary? How do they solve problems, represent information using only binary? Well, at the end of the day, if they want to represent 0 and 1, we need to do so physically somehow. And I dare say that maybe the simplest way to think about a bit, a 0 or 1, is like a light bulb. And so by human convention, let's just assume that if you are a computer, be it a laptop, desktop, phone, or the like, and you want to represent the number 0, you know what? You just keep a light switch off. You keep a light bulb off. If by contrast, you're that same computer and you want to represent the number 1, you take that same switch, that same light bulb, and just turn it on. So a light bulb that's on represents a 1, and a light bulb that's off represents a 0. So why is this relevant to computers? Well, at the end of the day, you and I are charging our laptops or phones at night. So there's some like physical resource being replenished there, whether you're on battery or some power cord. And so inside of a computer are just thousands, millions of tiny little switches nowadays. You can think of them metaphorically as light bulbs, but they don't yet actually shine light. But there are tiny, tiny little switches. And those switches, if you've ever heard the term, are just called transistors. So like computers have millions of transistors that can either be flipped on to represent 1s or flipped off to represent 0s. And from that very simple mechanism, electricity is there or it's not, a 1 or a 0, computers can actually count obviously from 0 to 1, but it turns out even higher if they use a little more electricity as well. So how might I do this? Well, let me go ahead and propose that I just grab one of our own light bulbs here on stage. This one's off. So for instance, if this were miniaturized inside of your Mac, PC, or phone, this would be a transistor. And indeed, here's the little switch on the bottom. And if your computer wants to represent a 0, it just leaves the switch off, and the light is not shining. If you want to represent a 1, well, now I've counted as high as 1, because the switch is now on. I've grabbed a little electricity. I'm holding on to it inside of the computer. And so now I see that this is a 1. All right, but unfortunately, with just one switch, one light bulb, I can only count from 0 to 1. How do I count out higher, might you think, intuitively? Say again? Yeah, so more light bulbs. So let me do this. Let me just grab something to put these on so I can use a few of them at a time. And let me propose that here, instead of having just one light bulb, let me give myself maybe 3 in total. So all of them are initially off. And if you think of this in miniature form in your mind's eye, this is like a computer with 3 transistors, 3 switches, representing now the number you and I know as 0. Why? They're just all off. So how does a computer go about representing the number 1? Well, it turns on one of these light bulbs. And how does the computer represent the number 2? Well, you might think, if I may, you just turn on a second light bulb. And if you might think, how does a computer represent 3? You just turn on the third light bulb. And so as such, with 3 bits, a computer would seem to be able to count from 0 on up to 1, 2, 3. But it turns out if I'm a little smarter here, I can actually count higher than that. Why? Well, I'm just considering like the combination of bulbs being on here. What if I do something like this? This is still 0, I will claim. But what if I propose now that this will be how a computer represents 1? On, off, off. This, though, will be how the computer represents 2. Notice I didn't turn on the same 2. I'm just turning on the 1 in the middle. This, I now claim, will be how a computer represents 3. This is going to be, in just a second, how a computer represents the number we know as 4. And yet I'm still only using 3 bulbs. This is going to be the number the computer represents as 5. This is going to be how the computer represents the number 6. And then lastly, it turns out with 3 light bulbs, if you're smart about it, you can count, it seems, as high as 7. Now, even if you kind of lost track of like what I was turning on and why, I claim there were 8 different patterns, from all of them off to all of them on. But notice that I started to permute them. I took into account which ones were on and which ones were off. Why, though, do these represent the numbers we know as 0 through 7? Well, let me go ahead and maybe let's do this. Instead of just considering there to be light bulbs, let's assign some special significance to each of them based on where it is. And maybe for this, could we get maybe 3 volunteers? 3 volunteers? OK. You're being volunteered. OK, come on up if you want to go over to the stage there. Yeah, you want to come on up as well? And over here as well. So there's some stairs on either end. Maybe a round of applause for our first volunteers of term. All right, so you are number 1. And if you want to go ahead and stand roughly right here, how about you want to be number 2? OK, come on over and right to the right of here, and you'll be number 4, it turns out. And if you want to come over here on this end, let's give you all a moment to introduce yourselves briefly to your classmates if you'd like.
Hi, I'm Ellie. I'm a senior.
Nice to meet.
I'm Rayhana, and I'm a first year.
Welcome.
Hi, I'm Joseph, and I am a first year.
Welcome. All right, so glad to have all 3 of you up here. Thank you. Let me propose now that we'd like you 3 to represent, how about the number 0? And I claim now that if each of you now represents a switch, you have sort of fancier light bulbs now. 1 is a 1, 1 is a 2, 1 is a 4. But each of you still just has a switch on the bottom, in fact, of your plastic devices. I claim these 3 volunteers are representing the number 0. Let me ask you all now, how might you represent the number 1? How should you cooperate here? OK, so we would have on, off, off, which I think matches what I did with my 3 light bulbs as well. If you want to go ahead and turn yours off, how might you all 3 represent the number 2? OK, so off, on, off now, from right to left. How would you 3 represent the number 3? So that's why my 2 light bulbs went on at the end. How would you 3 represent the number 4? Perfect. Number 5? Number 6, and number 7. All right, and give us one more. How would you represent 8? OK, you can't. How about then one more volunteer? One more volunteer. OK, come on up. All right. What's your name?
My name's Moeen.
If you want to say it there.
My name's Moeen.
All right. And Moeen, you're going to be number 8. And if now you all actually, let's make this. How would you represent number 8? All collectively as 4 bits or 4 switches. OK, 8. And now lastly, give me 15. Everyone's awkwardly doing arithmetic in their head. Oh, using unary. 8, yeah, is everyone? 8, yes, OK, round of applause. OK, thank you all. If you want to leave your numbers over here, we have a CS50 stress ball for you. But thank you for volunteering. You can turn those numbers off and leave them over here. So thank you. So how do we go from there to creating these patterns? Well, even though we still had 3 bits initially and 3 switches, later 4 bits and 4 switches ultimately, we still used the same approach fundamentally to actually representing information. And now why were they those patterns, and why did I very deliberately have our volunteers line up in that way? Well, I wanted them using base 2, aka binary. But with binary, there come certain rules. And even if you're not familiar with binary beyond that it exists and relates somehow to computers, it's actually pretty much identical to the system you and I use every day, known as base 10, aka decimal. So let's consider, if you will, by rewinding to primary school for just a moment, like how decimal works. And you'll see that even if you're not a computer person, you actually are. You just have to tweak your mental model ever so slightly. So here is the number that you're probably viewing as 123. But why is that? Well, it's not really 123. This is just a pattern of 3 symbols on the screen. 1 1, 2, 3, and your mind is sort of rapidly assigning mathematical meaning to them, 123. But why is that? Well, if you're like me, you probably learned back in the day when you have a 3-digit number like this, the rightmost number is in the ones place, the middle digit is the tens place, the leftmost digit is in the hundreds place. And why is that relevant? Well, if you then quickly do some mental math, as you and I just do instantly nowadays, that just means 100 times 1 plus 10 times 2 plus 1 times 3, of course, 100 plus 20 plus 3 gives us the number you and I know as 123. But beyond that, how do we get to just 2 digits instead of as many as 9 in the decimal system? Well, let's generalize this. In the decimal system, you and I know if we've got 3 digits represented by these hashes here, yes, it's the ones place, tens place, hundreds place, and if we keep going, thousands, 10,000s, and so forth. But why is that? Well, base terminology is now a little more germane. That's technically the 10 to the 0th column, the 10 to the 1, 10 to the 2. So these are powers of 10, where 10 is your base. Computers just simplify things a little bit, because computers at the end of the day only have access to electricity on or off. They don't have access to like 10 different types of electricity, just 2 on or off, if you will. Well, they just use a different base. And the rightmost digit would be in the so-called 2 to the 0s. Then the middle digit is 2 to the 1. The leftmost is 2 to the 2, aka 1's place, 2's place, 4's place. And as we kept going, 8. And if we keep going, 16, 32, 64, 128, and so forth. But the idea is fundamentally the same. So why is this how the computer represents the number you and I know as 0? Well, off, 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 from right to left, or in this case, left to right, is just 0. Why? Because that's 4 times 0 plus 2 times 0 plus 1 times 0 is, of course, 0. This is why 0, 0, 1 represents 1. This is why 0, 1, 0 represents 2, and 3, and 4, and 5, and 6, and 7 on up. And why did we need a 4th bit to represent 8? Well, we kind of needed to carry the 1, so to speak, using our familiar human terminology. But for that, we need a 4th bit, another transistor. And this now represents the number 8. And that's why we ended with on, from left to right, off, off, off. So I keep saying on and off, or the light bulb is on or off. But really, I just mean 1 or 0. And so computers and we humans think of things digitally as just being 0s and 1s. But mechanically, you can think of it indeed as these light bulbs. Now, a bit's not very useful. Even 3 bits, 4 bits, not that useful. You can count to 7 or 15. Generally speaking, bytes are a more useful unit of measure. And anyone familiar? How many bits is in a byte? Yeah, so 8 bits are in a byte. You can think of it as an octet equivalently. In some contexts, there are nuances there. But think of a byte as just being 8 bits. And that's just a more useful measure. So what does this mean in real terms? Well, if you've ever downloaded like a music file or a photograph or a video, those are measured in bytes. Probably not small numbers of bytes. Probably kilobytes for thousands of bytes, megabytes for millions of bytes, gigabytes for billions of bytes, especially for video. That just means you have a lot of patterns of 8 bits, some combination of 0s and 1s on your computer's hard drive. Here then, with a byte of bits, 8 bits is how a computer would typically represent the number 0. And if that same computer uses all 8 of its bits, its full byte to change it to 1, anyone who's quick with math or have seen this before, how high can a computer count with 8 bits or 1? Yeah, 255. Why is that? Well, we're not going to turn this into a constant math exercise. Indeed, after today, we're not really going to think about or talk about bits at this low level. But this is the 1's place, 2's, 4's, 8, 16, 32, 64, 128. And if I do all of that math from left to right, that indeed gives me 255. It ignores how we might represent negative numbers, but perhaps more on those some other day. But computers, of course, do so much more than numbers and math and all this low-level stuff. We send text messages, write documents, emails, and the like. So how might a computer represent something like the letter A? I claim at the end of the day, your Mac, your PC, your phone just has lots of transistors, lots of switches that it can use in units of 8, in units of bytes. How, though, if it's already using those patterns of 0s and 1s apparently to represent numbers from 0 on up, how do you go about representing letters of the alphabet, might you think? Yeah. OK, so we could assign a number to every letter. OK, so let me just conjecture. Well, let's just call A 0 for simplicity, B 1, C 2. And now let me play devil's advocate. OK, how do I now represent 0 or 1 or 2? Well, we've maybe created a problem for ourselves. If now we have to steal some numbers to represent letters, we kind of have to pick a lane. But there's a solution to that too that we'll see. And it turns out the world is not quite as simple as A being 0. A typically is represented by computers everywhere, phones everywhere, with the number 65, the decimal number 65. Using 8 bits, if we turn some of the zeros to ones, let me just stipulate, you can represent the letter A using 8 bits by turning certain ones on and certain ones off. But we will try not to focus on that binary level too much. So if A is 65, it turns out that B is going to be 66, and C is going to be 67, and so forth. And so where does that get us? Well, it turns out there's a whole system that maps numbers to letters. And here, as I alluded to verbally a moment ago, is the pattern of zeros and ones via which you'd represent 65. And just quick check here. We won't constantly do math. Ones place, that's easy. 2s, 4s, 8, 16, 32. 64's place, so 64 plus 1 gives us 65. So once I do that, how do I get to all of the others? Well, it turns out a bunch of Americans years ago came up with this, ASCII, the American Standard Code for Information Interchange. Now, what does that mean? Well, it's just an acronym describing what really you proposed, a mapping between numbers and letters. Not quite as simple as 0, 1, 2. Starts at 65, 66, 67 for capital letters. But here are most of the letters in use today, at least with this system. So this is just a big chart from online. And you'll see in the middle of this chart here, here's my 65A. Here's my 66B, C. And let's see, 72 is H. 73 is I, and so forth. So there's a mapping, at least for English, between all of these numbers and all of these letters. And if we focus here, those are the beginning of our uppercase alphabet. So suppose then that today, tomorrow, you receive a text message from someone. And underneath the hood, now that you're a computer person, you figure out a way to see what pattern of zeros and ones was sent. In this case, it's wireless as opposed to wired, but it's still some pattern of zeros and ones. And your phone is turning some switches of its own on and off to represent that message from a friend. Suppose that the 3 patterns you received were these 3 bytes from left to right, spelling out a 3-letter word. Well, if we do out the math, 1's place, 2's place, and so forth, I'll spoil it for you. Suppose that you received a text message that doesn't literally say 72, 73, 33, but you received a pattern of 8 plus 8 plus 8, 24 bits that, if you do out the math, represent the decimal number 72, 73, 33. Anyone recall what message you might have received from the green and white charts? Yeah. Hi. But yes, hi is the message. But 72, 73 gives us H and I. What's 33? Any guesses to 33? Yeah, over here. Yeah, so it's an exclamation point. How would you know that? Well, you really do need some kind of cheat sheet, aka ASCII in this case. And if we look elsewhere, let me highlight the left of the chart. You can see that next to 33 in decimal is indeed the exclamation point. So back in the day, a bunch of humans got in a room, decided that, hey, when we start building PCs and later Macs and phones, we all just have to agree on this form of representation of letters of the English alphabet in this case. We just need to agree on this mapping. But somewhat curiously, notice this. It turns out that once you paint yourself into this corner and start using 65 for A, 66 for B, well, how do you represent 65 the number and 66 the number if you want to do math or use Excel or something like that? Does anyone kind of see the solution perhaps? How do you represent the number 1 in ASCII? Yeah, in the middle? Yeah, so this is getting a little maybe Inception or something, but you could represent numbers with other numbers. And so if you want to represent the number you and I know as 1, like when you type it on your keyboard, turns out the computer stores that as the decimal number 49. If you hit 2 on your keyboard, the computer's not storing 2 per se. It's storing the decimal number 50. Now, thankfully, the paradox kind of stops there. We just have a mapping now of numbers to numbers. But really, at the end of the day, and you're going to learn this when we start writing code in that other language, C, next week, it's just context dependent at the end of the day. Inside of your Mac, PC, and phone, there's just all of these permutations of bits, all of these patterns of zeros and ones. And generally speaking, when you open up a text message, that you've received from someone. It's zeros and ones, but obviously if it's a text message, the whole point of text messages is to send text. And so those patterns of zeros and ones by default will typically be interpreted as letters of the alphabet. So you won't see zeros and ones, you won't see decimal numbers, you'll see the English message that your friend intended. By contrast, if you open up something like Excel, that same pattern of zeros and ones might indeed work out to be 72, 73, 33. You might see cells in your spreadsheet with literally those three numbers. Why? Because spreadsheets are all about numbers and number crunching and math in many cases. If by contrast you open up Photoshop and try to look at that same pattern of zeros and ones, it's not going to be 72, 73, 33. It's not going to be zeros and ones. It's not going to be high. It's going to be some color of the rainbow. You're going to use those patterns of zeros and ones, it turns out, too, to represent colors. And indeed, so long as you and I just agree, as humans long have, what these patterns are going to be, all of our systems, many of our systems nowadays are indeed interoperable. But I'm being very biased here. And indeed, the A in ASCII is very American-centric. What do you not see in this chart? If you speak any other language than English, odds are you're not seeing characters you know and love and need every day to type or send messages. Well, there's a huge character set that's not supported here, whether it's accented characters and a lot of Asian alphabets. You have many more symbols than can fit even on this screen here. And so humans kind of painted themselves into a corner early on, or really Americans did. But on a typical keyboard, US English keyboard, yeah, you have A's and B's and C's, uppercase and lowercase. But you also have accented characters here. And nowadays, not sure if this is maybe necessary, but nowadays you have other characters on your keyboard like these. And these are kind of a playful incarnation of what's actually a technical solution to this problem. If I claim for the moment that ASCII historically used 7 bits to represent letters, and let's just round that up to a byte, 8 bits to represent letters, ASCII can represent as many as 255, or really 256 total characters. Why 256? Well, if you have them all 0, that's 0. And the highest number I claimed a moment ago was 255. So that's 256 total possibilities. That's not many letters. It's fine for English, but not a lot of human languages. So what might the intuitive solution be if you want to represent accented characters, Asian characters, emoji, even like these, which are just keys on a keyboard nowadays? What's the intuitive solution if a byte's too few? Yeah. Yeah, so add another digit. Just like we had a 4th volunteer come on up to give us a 4th bit, let's just throw hardware at the problem and use a few more bits. So maybe instead of 1 byte, let's use 2. Or heck, let's use 3 or 4 bytes. Even though it's getting a little expensive, we're going from 8 to 16 to 24 or 32 bits. That's how computers do things these days. And thankfully, we have so much memory inside of our computers and phones, we can certainly spare a few to represent these things. And the solution then to ASCII is what we'll call Unicode. So Unicode is also just a mapping of letters to of numbers to letters, but in many different languages. And indeed, the Unicode Consortium is a bunch of people from all different companies and a lot of different companies and countries and cultures whose mission as an organization is to capture digitally all forms of human language in this case, and to ensure that especially smaller demographics of humans speaking lesser known languages are nonetheless represented and preserved digitally using some mapping of these zeros and ones. It turns out, though, if you start using 32 bits, as many as 32 bits to represent characters on a keyboard, that's 4 billion possible permutations of zeros and ones. That's way more than we need for most human languages. So there's a little bit of room in there for some of those more playful things, like those emoji. So for instance, suppose you got a text message with this pattern of zeros and ones. Or if we do out the math, suppose you receive a text message that if you do out the math in decimal is 4,036,991,106. Anyone know what emoji you're looking at? It'd be weird if you do, but what is this? Well, it turns out that as of this past year, this is the most popular emoji to be sent by many measures, face with tears of joy. So that is the pattern that a bunch of humans in the Unicode Consortium decided would represent this. But you'll notice many of you might have iPhones, some of you might have Android devices too, and sometimes these don't actually look quite the same. This happens to be the current version of face with tears of joy on iOS. On Android, it tends to look a little something more like this. And here's kind of a curiosity. even though you and I look at these things and they look like images, they're not images. They're characters, at least as we've defined them now in Unicode. And iOS and Android and Windows and Facebook and other companies and apps nowadays really just have different fonts, if you will. So just like fonts with English and other languages can give you different characters with serifs or not, emoji are themselves, yes, drawings that someone made, but they're really just a font. And so that same pattern of zeros and ones might just render slightly differently on someone's phone or another. If you've ever gotten like an icon on your phone that's broken and you've been sent an emoji, but it's like a square or something arbitrary and not sensible, it might just mean that you have not updated to the latest version of iOS or Android, which just updates the font of supported emoji, because those folks at Unicode pretty much every year nowadays are adding more and more emoji to that particular character set. Now, I went down the rabbit hole figuring out the other day just which are the most popular emoji these days. On Twitter specifically this past year, the most popular emoji, by contrast, was loudly crying face. I don't know if that says more about 2021 or about Twitter, but you'll see different trends certainly in how these are used. But even humans themselves didn't necessarily think 2 steps ahead.